Can you still see my screen?
Yes.
Yeah, okay. So after this general introduction, I will let Bruno from Club SWAC make the presentation on SWAC technology. I can show it, Bruno, or you take the lead as you wish. If it works. Yes, so now it's recording. Okay. Can you still see my screen?
Yes.
Yeah, okay. So after this general introduction, I will let Bruno from Club SWAC make the presentation on SWAC technology. I can show it, Bruno, or you take the lead as you wish. Bruno?
Yes, I'm going to take the lead if you don't mind.
Yes, please. Okay. I stop mine.
So, hello everybody. I'm going to tell you about the SWAC technology. So the principle is that the sun only heats the surface water, which is called the photic zone. So the heat that is transferred to the deep water is transferred either by convection or conduction. And we have a huge ocean convection that goes from the equator to the poles. And that is due to the fact that the cold water is more dense than the hot water. And therefore, when the water is cooling, it's going to the deep sea, and when it's heating, it's going to the surface. The general scheme of a SWAC is it's a matter of pipes. It's a huge pipe that is the intake pipe, a pump that allows water to circulate inside this pump, one outtake pipe to release the water that has been warmed, one heat exchanger that you see in gray here. The heat exchanger is made so that the cold water that goes inside the building is fresh water and not salted water, in order not to have problems of corrosion inside the building. And we have also auxiliary chillers, and we are going to talk about this later. The sizing of a SWAC. A SWAC must be sized for the load base, and I'm going to explain this more in my second presentation about research and development. There are many different types of SWAC. The most classical SWAC is the tropical deep SWAC, because in tropical oceans, if you go 1,000 meters deep, the water is between 4 and 5 degrees Celsius. So the deep tropical SWAC will pump this deep water and use it directly to cool the the cold water loop in the building. We have another type of SWAC that is the mountain lake SWACs that use the fact that the cold water during the spring is more dense than the water of the SWAC, and therefore it goes to the bottom of the sea, of the lake, and this cool water in the bottom of the lake can be used during the summer. We have moderate climate semi-deep SWACs, which are the ones that will be the most useful on the channel territories, that goes from 20 to 100 meters. These SWACs can the water is hotter than the air during the winter and colder than the air during the summer. So it can be used either directly or used with a heat pump in order to enhance the temperature difference. There is a specific case about inner seas like Mediterranean Sea, but I'm not going to go deep inside. And there are some shallow water SWACs that take the water really in shallow water. The environment impacts of a SWAC are very small, but even if they are very small, it's something, if we create a SWAC, it's because we have a strong environmental feelings, and even these small impacts, we need to take care of them. The first type of impact is the impact during the works. When there is works in the sea, there are two types of impacts that can be that can happen. The first type of impact is if there is mud that goes inside the water, the water will not be clear anymore, and it might be a problem for photosynthesis. And the second one is the noise that we make inside the sea. So for these two impacts, we in our project, we are looking at the time when we could have this kind of impact, and we have two things. We reduce as much as possible the size of this impact, and when it's not possible to avoid this impact, we use environmental procedures so that the impacts do not affect too much the marine beings. The other impacts are during the lifetime of the SWAC. The thermal impact of the release water, the water that we are going to release is not exactly at the same temperature as the sea all year long, and therefore we modelize the flow of this water to see what will be the impact, and to modify some parameters so that we can decrease the impact. And the last one is the chemical impact of release water, because water, deep water, is much more rich in nutrients, and therefore, if we if we don't take care about that, we could create an algae bloom. So the modelized flow will take care that that these nutrients go deep inside the water under the photic zone so that it cannot bloom the photosynthesis. And then there are co-products. There's a thermal co-product that is the enhancement of a chiller performance. If we have either negative chillers for freezing rooms, for example, or the chiller that will be used for the peak, they can be enhanced by the SWAC. We have agriculture and aquaculture that can use the fact that there's lots of nutrients in the deep water. We can, for example, create a mangrove in the desert with the SWAC using these nutrients. We can make seawater agriculture, cooled agriculture, for example, to raise strawberries in a tropical climate, and aquaculture. We can take out of the water and salt that are very popular in East Asia, and we can use this water for beauty and welfare, balneotherapy, and cosmetics. Thank you for your attention. If you have questions, I will be there in the end of the meeting to answer any of your questions.
Thank you, Bruno. We have a short video, a 5-minute video to explain again on the technology and its stakes with other words. I try to launch it and hope it works. So please let me know if within a few seconds you don't see the video.
Bonjour à tous et bienvenue dans cette nouvelle vidéo dans laquelle nous allons parler d'une technologie super intéressante qui utilise l'océan pour vous faire respirer. Mais attention, pas respirer genre avec vos poumons, mais tout simplement en vous donnant de l'air frais lorsqu'il fait trop chaud. En fait, il faut savoir qu'avec nos émissions de CO2 rejetées dans l'atmosphère depuis la révolution industrielle, eh bien la planète, elle est en train de se réchauffer. Le changement climatique, je pense que maintenant vous êtes au courant. Et du coup, on est dorénavant confronté à deux gros problèmes. Faire face à la hausse des températures et diminuer notre consommation énergétique. Sauf que pour éviter d'étouffer au soleil, eh bien nous utilisons très souvent de la climatisation, ce qui peut malheureusement consommer pas mal d'énergie. De fait, différentes personnes s'inquiètent de plus en plus de ce qui va se passer dans le futur vis-à-vis de notre capacité à faire face aux vagues de chaleur sans exacerber encore plus le problème. J'ai chaud donc je mets la clim, sauf que la clim ça peut relâcher pas mal de CO2 et donc mes petits enfants auront encore plus chaud. Du coup ce cercle vicieux, eh bien il y a beaucoup de gens qui essayent de le briser à l'heure actuelle en cherchant de nouvelles alternatives à la climatisation traditionnelle. Et parmi celles-ci, il y en a notamment une super intéressante qui va utiliser l'énergie marine. On l'appelle la technologie SWAC, pour Sea Water Air Conditioning, et qui est une climatisation à l'eau de mer. Alors pourquoi utiliser de l'eau de mer, me diriez-vous? Eh bien tout simplement parce que l'océan dans sa globalité, il est super froid. Et là je ne vous parle pas des plages bretonnes à 12 degrés, mais de températures bien plus basses. Car en fait, si à la surface celles-ci peuvent varier de plusieurs dizaines de degrés en fonction de l'endroit où on se trouve, eh bien en dessous de 200 mètres de profondeur, il fait en moyenne autour de 4 degrés. Ce qui est très très froid, et qui peut donc être utile. Car c'est là toute l'idée de la technologie SWAC, pomper cette eau de mer profonde naturellement frigorifique afin de l'utiliser pour créer une climatisation moins gourmande en énergie. Pour la faire fonctionner, rien de plus simple. Première étape, on récupère de l'eau de mer froide et on l'achemine jusqu'à un échangeur thermique où celle-ci va refroidir un second circuit d'eau. Celui-ci sera alors renvoyé vers divers bâtiments pour la climatisation et l'eau de mer utilisée sera par la suite libérée dans l'océan. C'est quelque chose qui est vraiment en train de se développer autour de la planète, notamment dans les zones près de la mer et où il y a une forte demande de climatisation. Par exemple à Hawaï, où l'île est vraiment paumée en plein océan Pacifique, eh bien la plupart de la production électrique, elle vient énormément des énergies fossiles. Du coup, utiliser le froid naturel des profondeurs pour faire des économies sur la climatisation qui est plutôt utilisée dans le coin, eh bien ça intéresse de plus en plus de monde. Cependant, si je vous parle de cette technologie, c'est aussi parce que ceux qui réfléchissent à son installation font très attention aux impacts sur l'océan. Parce qu'en fait, pomper de l'eau de mer et ensuite la rejeter à la surface, eh bien c'est quelque chose qui n'est pas aussi simple à faire si vous voulez laisser l'environnement intact. En fait, il y a principalement deux choses auxquelles il faut faire attention. La première, c'est tout simplement la température. Si l'eau de mer qu'on utilise pour refroidir le système se réchauffe trop, eh bien lorsqu'on va la libérer dans la mer, ça peut causer divers soucis. Car il y a pas mal d'animaux marins qui sont très sensibles aux variations de chaleur, donc il faut vraiment réfléchir à où on va rejeter cette eau de mer par la suite. Il faut faire par exemple très attention à ne pas libérer de l'eau chaude dans un courant froid et le faire dans une zone où tout se mélange bien, afin de ne pas créer d'anomalies de température. Mais du coup, il est tout à fait possible d'éviter tout problème avec une bonne connaissance locale du terrain et de la courantologie. Ensuite, il y a une autre chose un petit peu plus subtile à laquelle il faut faire attention avec cette eau de mer qu'on va pomper, c'est tout simplement sa composition chimique. En fait, il faut savoir que dans l'océan, l'eau profonde, elle est beaucoup plus chargée en nutriments que celle près de la surface. Du coup, si vous pompez cette eau profonde et que vous la rejetez sans réfléchir à la surface, eh bien vous envoyez en réalité un véritable festin à un paquet d'organismes marins. Ce qui peut vous sembler cool sur le moment, mais qui en réalité ne l'est pas du tout. Car cela peut provoquer des proliférations incontrôlables de certaines algues, c'est ce qu'on appelle de l'eutrophisation. Et c'est notamment ce qui se passe en Bretagne avec les marées vertes. Et Dieu sait qu'on n'a pas envie que notre climatisation fasse la même chose. Mais en fait, ce problème, on peut aussi l'éviter. Il suffit de bien choisir la profondeur à laquelle on va libérer cette eau. L'idée, ça va être de le faire en dessous de ce qu'on appelle la couche euphotique, c'est-à-dire la zone dans laquelle il n'y a plus assez de lumière pour que la photosynthèse fonctionne et où donc les algues ne peuvent plus se développer. Du coup, si on fait ça et que cette eau reste bien en dehors de la surface, et bien normalement, il n'y a pas de problème. Ce qu'il faut comprendre, c'est que sur le papier, cette technologie SWAC, elle pourrait apporter beaucoup dans le futur si la planète continue de se réchauffer aussi rapidement. L'eau froide de nos océans est une ressource vraiment propre qui ne demande qu'à être utilisée, mais en utilisant nos cerveaux. En prenant le temps de comprendre comment cet écosystème marin fonctionne et en continuant de l'étudier, il apparaît tout à fait possible de faire les choix les plus judicieux dans le futur pour les hommes et les poissons. De ce qu'on m'a dit, ça ne coûte par exemple pas excessivement plus cher de libérer l'eau du SWAC à une profondeur qu'à une autre, mais ça par contre, ça peut avoir une importance primordiale pour certains animaux. L'installation de cette technologie semble donc tout à fait compatible avec la préservation du monde marin, il faut juste s'assurer que cela est fait avec toute la bonne volonté du monde. Pour vous donner une idée, certains projets SWAC, ils font même attention au bruit lors de l'installation et de l'entretien des structures pour ne pas déranger les mammifères marins. Donc sur ce genre d'initiative, il est tout à fait possible de veiller au bien-être de l'océan, pour cela, il suffit juste de s'en donner la peine. Je tiens particulièrement à remercier les différentes personnes et organismes qui m'ont aidé à réaliser cette vidéo, afin de vous présenter la technologie SWAC sous toutes ses coutures. Car parler d'une technologie cool, c'est bien, mais aussi mentionner ses impacts négatifs, si le travail est mal fait, c'est mieux. Comme d'habitude, si cette vidéo vous a plu, n'hésitez pas à me le faire savoir juste en dessous, je pense que vous connaissez le chemin. Sur ce, on se retrouve très vite pour une prochaine vidéo. Ciao.
So, I hope you enjoy this short pedagogic video. I would like now to tell a few words on the genesis of the project. So I will go. Okay, can you hear me and see my screen again?
Yes. Can you put it on full screen?
It's in full screen now.
Perfect. Yes. Thanks.
Yeah. Okay. Yeah, so the genesis of the Euroswac projects come from first studies we have made for the channel tunnel, and that have shown that we could save up to 30% of power consumption to cool down the tunnel, which need some air conditioning due to the effect of the trains within the tunnel. And so we have made first studies for the UK side of the tunnel, which need is around 25 megawatt thermal megawatt, and thus saving 30% of electricity when you consider the energetic mix in the UK. It allows to save about 1,250 tons of CO2 per year. So based on this, we have organized a strong partnership with the French and UK partners. You can see on this slide. We as EDF are bringing some engineering capacity and coordinating the partners. We have the De Profundis, who is a French startup represented by Bruno, who is specialized in SWAC technology. Eurotunnel, of course, has possible end users, and I will tell a word about this later. We have the Club SWAC France, which is an organization which is helping on the communication and the network dealing with SWAC technology. We have academic partners, the University of Exeter and the French engineering school ENSTA Bretagne, based in Brest, who are developing some ways to optimize the technology, and also making a market study to see opportunities on both sides of the channel. We have specialized engineering companies in offshore methods, Doris Marine and cette Hydratec on French side, and the Stat Marine, which is a subsidiary of Doris Group for the UK part. And for all the environmental studies and permitting studies, we have the support of Royal Haskoning DHV. And this project is supported by the European Union because of many four characteristics: its innovativeness, its positive environmental impact, the French and UK partnership we have organized, and the replication potential for the channel area. So this is why last year in June we had an agreement from Interreg France Channel England program, allowing up to 8.9 million euro co-funding from URDF fund, so it's a European Regional Development Fund, over an overall project budget of a bit more than 20 millions for a project which shall terminate before March 2023. Now I come to a main issue we have at the moment. It's the question of having a demonstrator for the technology in the channel area. So as you understand, we were supposed to develop the project for the channel tunnel, but due to the COVID, as a consequence of the COVID, we cannot build the project in the constraint time we have of March 2023. So we are clearly looking at the moment for an alternative prototype somewhere in the channel area to develop. And that's why also we expect that this meeting will help us to find some potential end users that may enter the partnership, and we can find a prototype to develop. Now I will let Ola from the University of Exeter develop the market opportunities we see. You want to share your screen, Ola?
Yes, I'm doing it right this moment.
Okay,
Just let
thank
me
you.
know when you can see it.
Can see it.
Perfect.
Not anymore.
Cool. Let me.
Okay, now we can see it again. Not anymore.
And now.
Now we can see it again.
Yes.
That's great. Let me know when you cannot see it again. Good morning. Bonjour. My name is Ola Zavalnagier and I'm representing University of Exeter. Before I start my presentation, I would like to introduce others who also contribute to this study. So I'm working with Ajit Pillai, Alan Alexander and Lars Johanning from University of Exeter, and Jean-Yves Pradion from Insta Breton. So what we are trying to achieve with the seawater air conditioning SWAC system is to design and validate the system in the channel area, so it's cost efficient, competitive when you compare to conventional cooling system, is of course innovative, but also it's eco-friendly, it's sustainable and replicable at other sites. In the conventional cooling system, you always have to use the refrigerant. In our case, this refrigerant would be the channel C cold seawater, which is widely available renewable energy source. Our preliminary study shows as well that this system will reduce CO2 emission and definitely will use smaller land than it's used for the conventional cooling systems. To study it, we need to analyze a few aspects. First of all, we need to learn about the resources. So we need to learn about the availability of the source. We need to identify the potential users, potential sites. Once the sites are identified, we'll analyze them in two different aspects, environmental and technical. Once this is done, we will check the site accessibility. What would be the estimated electricity usage and what usage is applied now, and also what cooling capacity is required. Then we'll go to SWAC design and we will try to optimize some components. So we identified 4 components of the SWAC design which can be optimized, and these are the intakes pipes, outlet pipes, technical building, and pumps. And each of those 4 components have all the components to optimize. So with the intake pipes, it's the numbers, length and diameters, materials it's made of, flow rate, filters. With outlet pipes, it's depth, intermixing zone, length, release velocity, drainage pipes, maybe if they are existing can be used again. Technical building is again, it's about location, size, heat exchangers, auxiliary chillers, and operation and maintenance. And with pumps, it's about all about number, the location, if it's offshore or onshore. Then if it is offshore, the depth of the pumps, power use, and operation and maintenance. Once this is all optimized, we will look at the cooling capacity of the SWAC model, its electricity consumption, and also carbon footprint left. We'll go into environmental scope, or maybe not later, it will run all parallel. So we have to understand the constraint parameters when it comes to environmental impact, and the 2 most important will be the thermal discharge and mixing zone definition. So where we are going to locate it, the mixing zone, where it will be. We will look into the UK and France regulations. We will look at the cost of environmental studies for the bigger projects, environmental impact assessment. Then we will ask a question, is it feasible? If it's definitely yes, we'll give it a green light and go for it. If it's definitely no, it will be red light. But then with the no, we will also see if it's improvable. And of course, if it is improvable, we'll give it an amber light and some potential for further optimization. Then we will assess the market opportunity. To do so, we will analyze the demand profile and also end users. And once this is done, we will validate its eco design. So with this, we will apply the optimization, and also we will identify the key criteria for replicability. Then we'll go into the system performance, and again we'll ask the question, is the system feasible? And if it's yes, we will definitely phase out the plan. If it's no, we will issue some mitigations. Then I already mentioned optimization a few times. So this is what we are going to apply, technical optimization. And the idea is there are three components. I mentioned already technical requirements, environmental studies. It's of course up to it also financial analysis. All of them are overlapping with each other, and in the very, very middle, we have the replicability. So hopefully by optimizing all of these three components, we will get a good criteria for replicability at all the sites we are going to choose. We are going to apply the genetic algorithm, and it will be the multi-objective optimization to minimize both cost and the environmental impact. Of course, we need to find some gold remedy for it. We probably will find a big difficulty to optimize, to minimize both. So we have those solutions here on this line, those red dots, and the golden solution will be somewhere in the middle, and it will be up to the stakeholders, shareholders, to decide when they want to move forward with the project. And finally, we are intent to apply innovative marketing approach. So at the moment, all of the businesses, it's all about the linear economy. So it's produce, use, waste. And of course, we cannot go like that for much longer with the world going like it's going. And we need to be innovative. And to do so, we will have to move into the circular economy. So move towards the approach when we produce, use, reuse, refurbish, remanufacture, recycle. So we will extend the life of the product. And to do so, we need to change a little bit of approach. It's a lovely idea, but there are loads of things we need to change. But this is why we're working on it. So our approach would be to run some economical and economic analytical models. We will focus on the corporate learning, so the training to show the end users, shareholders, stakeholders, different approach and how it can be cost effective and how it can be actually better than approach we are taking right this moment. We will include in this process users, shareholders, stakeholders, corporates, so they have a good, deep understanding what we are trying to achieve and how it will benefit them. We'll study effectiveness versus efficiency, scaling up versus scaling out, and resilience and regeneration. Thank you very much for your attention. If you have any questions, I'm ready to answer. Thank you.
Thank you, Ola. I just suggest we keep the questions after the presentations. We have one more presentation on the R&D developments to reduce the capex, and then again a presentation from you, Ola, regarding the demonstrator. So Bruno, if you can share for the presentation on R&D, please.
Yes. Can you see my screen?
Yes.
Okay, great. So I'm going to tell you about the the research and development we are working on in order to make cost reductions for the SWAC. First, I'm going to talk about the SWAC market. The worldwide AC consumption is equivalent of the production of 300 nuclear reactors. By 2050, AC will be the second largest electricity consumer after the industry. And yet, 10% of the world population lives within a few kilometers from the shoreline. So we see that if we want this AC to be green, SWAC can have a huge interest in the future. The SWAC challenges that will be addressed today, the first one is to reduce capex. The second one is to avoid cavitation issues. The third one is fit for purpose design. Then extended use of pumped water. And to finish, we are going to talk about the fact that it's water and not oil. The SWAC systems are very interesting because they are low carbon, environment friendly, and as they are predictable and load-based heat producing, they are also power company friendly. But the last endeavor is necessary to reduce the capex of the SWAC. The capex challenges are, as it's a very long pipe that goes into the sea, we have a high material cost. We have an expensive nearshore stabilization and a high cost of installation when we go deep. So the first thing I'm going to talk about is the new design for a low-cost SWAC. So we have we work on two projects on this part. There is a project that is close to the shore, that is the self-burying rigid pipes. That means that the pipe will have connected to it everything that can make it bury under the sand by itself. That means a reduction of the installation price and the reduction of the meteorological contingencies. And the second one is a little bit more far away from the shore. It's flexible pipe for deep water section. So if we have a 1 kilometer long, we can have a 1 kilometer long section up to 50 centimeters in diameter in one roll, and the cost is 25% smaller than HDPE, and it's very easy to install. If we think about this install, you see the boat, you see they have two rolls on the boat. The first roll has the pipe, the flexible pipe on it, and the second roll has a chain that is used to ballast the pipe. And then both of them are connected as the boat is going further. And so we have easy, fast, deep water installation of pipe using a dedicated laying cable for near vertical lay. Here you can see in the three parts in red are the parts that the cost that can be cut by using a flexible pipe. We have the pipe material that will be reduced, the deep water installation that will be reduced, and the shallow water installation that will be reduced. Then the self-bearing system. You can see that under the pipe there are three little pipes. One that is that is intaking a mix of water and sand, and two that are injecting high pressure water in order to soften the sand. On the right of the screen, you can see an animation of how it works with the valves. So second point is solving cavitation issues. The cavitation happens when the absolute pressure of a liquid is lower than a certain limit. There are three ways to solve the cavitation. The easiest way, but it's not very efficient, is to limit the water flow. Then you can see on the top drawing, you can dig a deep pit in order to have the pump that is at a level where the static pressure of the water is more important than at the surface. And the third one is to use a submerged pump. So what happens when we increase the speed of the water inside a pipe? As we increase the speed of the water, the pump creates an overpressure on the coast part of the pump and an underpressure on the sea part of the pump. Here we have reached the yellow line, and the yellow line means that the salt gas that are inside the water get undissolved, and this creates a mix between liquid and gas in the pump. And as the pump is not made for dealing with biphasic liquids, the performance of the pump will reduce dramatically. But for the moment, it's just a matter of performance. If we go faster, then we have something that is much more critical. We have cavitation. Cavitation means that the water itself will turn gaseous. This physical phenomenon is a very violent phenomenon where you can have locally temperature of several thousands of degrees, and this phenomenon can break completely the pumps. So let's see what happens if we create a pit or a submersible pump. By digging, by having the pump more under the surface water, we have the static pressure of the pump that increases, and then the problem of cavitation and of gas undissolution will disappear. And we can even now increase the speed of the water until the limit where the salt gas get undissolved. The following point is the fit for purpose design. We need to have a very accurate study of the client thermal needs for an optimal system dimensioning. I give you an example to see how the dimensioning of the SWAC will impact the profitability of the project. In the beginning, we installed SWAC capacity to be able to answer to 100% of the client needs in cold. That means that the SWAC is dimensioned for the hyper peak of cold demand, and therefore the energy provided is 100%. So what happens if we downsize the SWAC? You see that now we have downsized the SWAC by 1/4, and we have lost only 5% of the energy provided. That is the part in red. All the part in blue will be done with the SWAC. So the interest is to find an optimum, and our optimum in our example will be 40%, because with 40% of the installed capacity, we will still be able to produce almost 70% of the energy. Now we're going to talk about the extended use of water. First, in terms of thermal energy. The traditional ice water loops temperature is between 7 degrees and 12 degrees. We reject water that is 12 degrees, and this water is still cold. For me, I wouldn't go and swim in this water. So as it's still cold, it can be used more extensively to cool down. So we can we work on a different kind of loop that is 7 degrees to 17 degrees. That means that the SWAC power will be doubled without having to change the piping system. How can we do it? We can optimize the fine coils. That means that we increase the surface of these fine coils, and we can use things as a radiant chill sailing. Then we have the byproducts that can be used, but I have told about this on my first presentation. I will not tell you about this again. And last thing, it's water and not oil. We usually use in SWAC systems the oil and gas industry standards, but the oil and gas industry standards are made for an industry that is very much more that can generate much more pollution than SWAC. So it's important to work with the environmentalists and the experts of oil and gas industry to see which of the routes that are good for oil and gas industry must apply to SWAC and which are not necessary. So a cheap economic SWAC system is possible. Thank you very much.
Thank you, Bruno. So now that you have explained, oh, there is a lot of echo. I will let Ola develop the demonstrator opportunities we see, as you have explained now how we can optimize the design for a particular site and application.
Okay, so I'm back. Can you see my presentation?
Yes.
Yes.
Great. So I'm talking today about the demonstrator opportunity. So our aim is to test a seawater air conditioning system, a prototype for the shallow water based system within the channel area. And what we're offering is the study of energy consumption at a chosen site and the new cost-effective and eco alternative for cooling. We are aiming at the general interest group, so anybody who can disseminate our ideas, who can add to our research, who can spread the news about the new idea, but mainly we are aiming at the end users. So anybody who has a room which have to be temperature controlled, and it has and who has the access to seawater. So we're aiming at infrastructure and service providers, enterprise, and SMEs. And the idea is to find somebody within the channel area. So we have all of those all area here in blue, but of course it has to be close to the shoreline. And the idea is for containerized SWAC system. So it will look something like that, and it will be short-term demonstrator with somewhere within this area close to the shore. Lars, would you like to add anything?
Thanks, Ola. Yes, so I think it's really now for taking it over and bring it back to the participants really as well. And in terms of, we heard a lot about SWAC systems now whole this morning, but the opportunities, as Lauren introduced, because of COVID, as a demonstrator that was planned cannot go ahead as in its form. So the idea is really, as Ola just was saying, is developing a containerized SWAC system that can be demonstrated for a particular end user who has this cooling demand. I think so. We hopefully have some very interested companies here or organizations here in this event who potentially could become an end user, and we really would like to hear. I mean, as I said, we introduced the SWAC system. But we really would like to hear from you what your demands are, what are your requirements are, and then see how we could optimize the demonstrator for you. So the overall project really would look, of course, in terms of rolling out the SWAC system in a large scale along the coastline. But I said, this discussion here maybe should focus much more on a shorter term demonstrator, and we would like to see how we could engage with you and really making sure that we develop a demonstrator in a short time with you that proves the concept, and hopefully afterwards provides you also a solution for generating or providing the cooling or the carbon neutral level. So I think that's all what I would like to say, and I think it's important now to really go into the discussion So I really would like to open, I guess, the round for discussion. Unfortunately, I think so. Lauren, correct me if I'm wrong, but I think so. The chat box is still not functional, so we have to rely on people putting their hand up.
I see the chat box is working for some people because I see some comments on the chat. So I'm sorry if it doesn't work for everybody. So don't hesitate to raise your question directly orally.
One of the questions for us is particular which kind of demand you would have. This would be the first point of our demonstrator design, certainly. So what kind of particular demand you have, and then make sure that we can design it accordingly with a SWOC system. So I don't know if you have some particular participants here who have a cooling demand and who would be willing to share maybe their demand requirements.
We have a first question from Frank Roberts asking what timescales are you working to? The limit we have on the timescale is linked to the end of the Interreg France Channel England program, which is March 2023. So we are looking really to develop a prototype that we can build before March 2023. That's the idea.
And I think so if we add on this one, probably a demonstration phase, what is in a length of something like between 3, maximum, I guess 6 months, but really depending on the length of designing and manufacturing the demonstrator.
Someone raised a hand, but
I see Carly Daniels, you raised your hand.
Hi, yeah, I don't mind sharing our potential to be an end user. It's maybe slightly outside of the conventional air conditioning, although it might not be. But I work for the National Lobster Hatchery, and we run a containerized facility as well as a kind of a building-based facility rearing lobsters. And we often have issues with regards to keeping the water temperature to the correct temperature that we need. In the summertime, we need cooling systems to be able to do that. In our containerized systems, we have the ability to maybe cool through an air conditioning unit, so keeping the container at a set temperature rather than the water itself. But in our land-based facility, it is solely done through kind of water chillers as such. In the winter time, sorry, we have the opposite. So we obviously need the water to be raised in temperature, which I believe fits in quite nicely with what you were saying. One of the things I was thinking, and a question for you guys, I noticed that one of the issues or potential impacts was the raised water temperature that would then need to be released back into the water and the issues that it might cause. Have you thought that you could maybe use that the effluent in, say, an aquaculture production facility as well? So use an air conditioning unit in one building, and then maybe the effluent be used as a kind of a heating system for a slightly warmer water species that might be reared for aquaculture.
Bruno, you want to comment on this one, or you want me to comment on it?
Well, yes, of course. So it will all depend on the site, and of course we were thinking about it. It could be used in the aquaculture, but it will have to be all with the environmental impact assessment. So we will have to look into the zone mixing and all of those things. But yeah, absolutely, this is potential.
Cardi, can I ask? So the idea is to use this as an aquaculture rearing zone, let's say in this way, in a sea, or having another next to onshore rearing zone for aquaculture, where you're cooling the water before you're releasing it to the sea.
Probably the latter, actually. Another land-based facility that was aquaculture. I mean, you could link it to sea-based facilities, as Ola was recommending, as well. But I was thinking specifically of maybe a land-based aquaculture facility alongside another facility that you might be cooling.
And as a consequence, you can cool the water out and wouldn't have the impact to the environment.
Yeah, we'd potentially reduce the impact.
Yeah.
Yes, yeah.
Definitely the potential.
Yeah, I don't think we have considered this, but as what I was saying, I think it's something certainly that could be considered if the end user would have this kind of requirements to integrate this, as brings additionality as well to the project.
Okay.
We have a question from Mathieu Valette, who is asking if we have a minimum housing volume or number of people for such an installation, and also asking if we have think about producing hot air like the geothermy, meaning hot air in winter and cold air in summer. Maybe Bruno, can you answer to this?
Yes, of course. In the channel area, as we are not going to take the water from very deep, we have the limits for the small consumer are very small. As soon as we have 1,000 square meters, it's enough, or even 500 square meters. It can be studied. The second question was, I don't remember the second question, Laurent. I'm sorry.
It's not making only cold, but sometimes hot.
Yes, of course. As I said it, the water during the winter is hotter than the air, so we can use the seawater in order to raise the performance of a heat pump, and we have a coefficient of performance for heat pumps that are completely incredible. Like we have coefficient of performance that are more than 10 and even sometimes more than 15. So we can use it with a heat pump that will produce cold in summer and hot in winter.
Thank you. We have a question from Jennifer Roberts asking what is the predicted technology lifetime. I can try and answer to this. I think even if we are making some developments on how to reduce capex, we intend to use a technology which is a proven technology. I mean, the pumps that we would install are proven technology. The pipes material also. So clearly, I can give an example for designs we have made for such projects where we intend clearly up to 20-25 years. Of course, it will need some maintenance, but it's a long-term capacity. Now, this is for an industrial use in the end. For the prototype, we are not especially looking for something that will stay 25 years long. It can be really a short-term prototype just to prove the efficiency. I hope it answers your questions.
If I can add something to it as well, it's like, so we are thinking about 3 to 6 months prototype on a demonstration side. But of course, if it proves to be good and cost efficient, this is the potential for the site to maybe invest in it a little bit more and its deployment in the future.
Yeah. We have a question from Carly Daniels asking, what is the temperature of the effluent you are likely to need to release back into the sea? Again, Bruno, can you comment on the difference of temperature with the seawater?
Yes, of course. In fact, it depends on the country where you work. There are two things that are important. It's the environmental regulation, and then there is another thing. It's the environment study that tells you if even if you comply to the regulation, we don't want to harm the environment. So the environment regulation in England, I don't have the figures in my head. I will let Laurent tell about that. Okay, this is.
Yeah, I can comment. Usually, we try not to reject water more than around 30 degrees C, and not to have more than at maximum around 10 degrees C difference with the local temperature where we reject. And we try to also to see after a mixing with the environment, then within a few let's say around before 100 meters, the temperature would not exceed more than 2 or 3 degrees compared to the ambient temperature. That just to give typical figures, because this has to be checked carefully depending on the environmental impact assessment we would make. So it depends really on what are the species, if we have a particular species to take care of in the particular environment. Of course, this is something that our partner Haskoning has studied a lot for the prototype we were developing. So I've seen Sarah from Haskoning is here. She can develop a little more if she wants. But that's to give you some ideas on the difference of temperature we are talking about.
Thank you very much. Can I ask one more question? Sorry for all the questions. Is the salt water that's extracted from the sea treated in any way, or does it literally just go through pipes and then get released back out?
Sorry, it was a bit fast for me. Can you repeat?
Sorry.
I can answer this if you want to. For the demonstrator, it's no intention to treat the water. For long-term installation, chlorinization is considered, I think. So there was this one comment about this on one of the other slides. It's at least considered, because otherwise the fouling in the pipes could be quite significant over time, and it could cause failure. Again, this would be, need a detailed environmental impact study if that would be used. But the intention would be to avoid this wherever possible.
Yes, clearly, Lars, we keep in the design the possibility to have some chlorination, because it's difficult to guarantee that we will never need it. But we have a stronger design criteria to make everything possible to avoid chlorination. And I will give just a few main criteria is first the velocity within the pipes. So we try to keep a high velocity around 2 meters per second, and there are many studies showing that when you have a velocity within this area, you can prevent a lot the biofouling. We also use some pipe material that are that prevent biofouling, typically high density polyethylene pipe are known to be less subject to biofouling. Just to give you two main criteria we have.
I see a hand raised by Frank Roberts.
Hi, good morning. Can you hear me?
Yes.
Yes.
This is of interest to me. I look after a facility for the University of Plymouth called the Brixham Laboratory. I could, if the technology could work, I could share a picture which would at least help you to see what the facility looks like from the air. But let me see if I can do that. Can you see my screen?
Yes.
Yeah.
Can you see the picture of the laboratory?
Not yet. Yeah, I think so.
I'm not sharing the right thing. Excuse me a moment. Right.
Yes.
Has that worked?
Yes. Yeah.
Okay. So we currently the University of Plymouth owns this laboratory. It currently has the ability to abstract seawater from the bay beside us, not very deep, 6 or 7 meters deep. We have 2 seawater lines buried into the ocean floor. They come to a little pump house. Again, I don't know if you can see my cursor, but
Yes.
we have a little pump house here at the front of the laboratory, and it pumps the seawater out to the back and then distributes it around the site. It's used mostly for aquaculture or for environmental testing associated with aquaculture. The large building on the right is the newest building that went up 12 years ago. Also had the ability to use the seawater for cooling the air conditioning system. But it was never a system that got used. There were some initial issues with the seawater being corrosive to the pumps around that system. But it was a facility that was put in. This laboratory was owned until 2014 by AstraZeneca. So its main needs were for aquaculture. I think the ability to try to use seawater